Today I'm going to introduce you to the other major branch of statistical inference, confidence intervals. Confidence intervals use sample statistics to estimate population parameters, in contrast to tests of significance, which test claims about population parameters. Here we're actually trying to estimate what those parameters might be, what the value of those parameters might be. You might ask yourself the question, why can't we just use a particular number as that estimate? Why do we have to use intervals to do this? You could use p hat to estimate a population proportion p, or x bar to estimate a population mean mu. Why don't we just use these point estimates? Well, if you use a point estimate, you're going to hit the true target very rarely, and you'll be very lucky if you do. And you'll have no way of saying how sure you are of the estimate that you've made. So intervals have these advantages. They give you a better chance of being right, and they allow you to say how sure you are about the estimates that you make. Now, confidence intervals generally have this kind of format. They consist of an estimate plus or minus a critical value times a standard error of the estimate. Okay? Now, 2/3 of this formula right here will come from sample data. This estimate comes from a sample statistic. It's x bar or p hat, depending on the context you're working in, and that's always calculated from sample data. So this is something you'll be able to calculate from sample data. The standard error of the estimate is the standard deviation of the statistic. It's also calculated from sample data. Okay, so 2/3 of this formula right here will come from sample data. Where does the critical value come from? That's the big question. Where are we going to get that? And that's pretty much the key to what we're going to do with confidence intervals today. Now, suppose we want to estimate a population proportion p. Okay, in order to do that, you need to use the sampling distribution for p hat, which is the sample proportion. And you remember there were some conditions that we used or talked about when we were doing Unit 9. We were talking about this sampling distribution for p hat. And if those conditions were met, then this distribution for p hat would be normal, at least approximately. Okay? And then the critical value that we're going to use for our confidence interval is going to come from the standard normal distribution. In other situations where you're working with means or where you're working with chi-squares or something like that, then the appropriate sampling distribution will not be a z distribution, it will be something else. And when we get to those topics later on, we will see what the appropriate distributions are to get our critical values from. But for now, we're going to be doing inference for proportions, and we'll use the standard normal or z distribution for that. Now, here's how it works. Okay, you can decide how confident you want to be in the estimate that you make. You can say, I want to be 90% confident or 95% confident or maybe 80% confident. The critical value that you're going to use is going to depend on how confident you want to be. And you have complete discretion over that. You can choose that. Okay? This level of confidence, this C, it indicates how confident or sure you are that the confidence interval that we develop contains the true value of the parameter that we're trying to estimate. Another way to look at it, which appeals to a lot of statisticians, is to think of C, this level of confidence, as the fraction or the percentage of all simple random samples of a given size that will yield an interval that contains the true parameter. And I think that's the more common approach to confidence intervals, but it's not universally agreed upon, but that's the most common way of looking at it. You can choose any value of C that you want, but the most common ones are 80%, 90%, 95%, and 99%. Okay? Now, all we've done so far is we said, okay, to get this value of Z star, we need to choose a level of confidence first, and then the value of Z star will follow from that. Well, how do we get directly from that C to that Z star? That's what the next page here is going to talk about. And here we go. how to get from C to Z star. Okay, remember you get to choose C. Z star is going to follow from that. How? Well, it works like this. Okay, you choose a given value of C. You choose a value of C, and then Z star is the value for which the area under the Z curve, the standard normal curve, from negative Z star to positive Z star is equal to C. Let's look at a picture and an example. Okay, suppose you choose your level of confidence to be 80%. Okay, the Z star that we're going to use is this value here, so that the area under the curve between its opposite, negative Z star, and Z star itself is the confidence level, 80%. Okay, now if you wanted a higher level of confidence, you could move these Z stars out. If you want a lower level of confidence, you can move them in. Okay, but this boundary right here on the right, that Z star, is the critical value, and it depends on what C is. Okay, if we choose C to be 90%, well, then we have to expand these boundaries out a little bit so that we capture 90% of the area under the curve. And in order to do that, we have to increase this Z star to 1.645. If you want C to be 95%, well, you're going to have to move these boundaries out even further. And now the Z star that would be on the right would be 1.960. And if you look at the Z curve and calculate the area between negative 1.960 and positive 1.960, that will contain 95% of the area under the curve. Okay, I've calculated this for 90% too, but I won't put that in the picture. Let's just use this little table. Anytime you need to know what a Z star is for a given level of confidence, use this. Okay, for 80% confidence, 1.282. For 90%, 1.645. For 95%, 1.960. For 99%, 2.576. Now these Z star right here, this Z star is a certain percentile on the Z distribution. And that percentile is the level of confidence plus the area in the left tail there. For 80%, that's 10% to the left of that in that left tail. And 10 plus 80 makes 90%. So this is the 90th percentile of that distribution. On this one, if you go to 90% confidence, you'll have 90% in the middle plus 5% over there. That makes this percentile the 95th percentile. For 95% confidence, this would be the 97.5 percentile. And for 99% confidence, the right boundary would be 99.5 percentile. Okay, so that's how you can relate these confidence levels and these Z stars, these critical values, and these percentiles together.